A matrix is a rectangular array of elements. While there is no particular intuition, a matrix is a tool for computations. To understand this, let's consider vectors C and T on a plane. Vector C can be represented in vector form as shown. Vector T can be represented in vector form as shown. Alternatively, using matrix representation, we represent the vectors as shown. Next, we will consider the two vectors P and Q in three-dimensional space such as coordinate space. Shown are the vectors in vector representation. The matrix representation can be written as shown. When we write in the matrix form, in the given context, we presume that the matrix can be reversibly written in vector without loss of generality, in other words, without loss of information. Suppose a vector S is given in matrix form as shown. In the vector's context, we represent the vector as shown. A matrix is an ordered rectangular array of numbers or functions. The numbers of functions are called the elements or the entries of the matrix. Let's consider a matrix. Matrices are denoted with capital letters. In this matrix, each number is an element. The horizontal lines of the elements are called rows. This matrix contains 3 rows. The vertical lines of elements are called columns. This matrix contains 3 columns. There are matrices of varied sizes. The size is termed as order while referring matrices. The order of a matrix corresponds to the number of rows and columns the matrix has. In the matrices shown, the first matrix is of order 3 by 3, which corresponds to 3 rows and 3 columns. The second matrix is of order 2 by 3, which corresponds to 2 rows and 3 columns. The third matrix is of order 3 by 2. On generalizing, any matrix can be considered as a rectangular array of elements with m number of rows and n number of columns. The alternative representation of the matrix is as shown. The subscript ij for the element A indicates the position of each element in the matrix. I represents the row and j represents the column where the element is located. For example, the element A, 2, 3 represents the element in second row and third column of the matrix. The value of I varies from 1 to m. The value of j varies from 1 to n, where both I and j belong to the set of natural numbers. There are various types of matrices depending upon the elements present in the matrix. First, we will start with the column matrix. The column matrix consists of only one column. An example of a column matrix is shown here. In a column matrix, each row will have only one element. The matrix shown here is of order 3 by 1. The general representation of a column matrix having m rows is as shown. A matrix is said to be a column matrix if it has only one column. Similarly, a row matrix will have only one row of elements. A row matrix is shown here. In a row matrix, each column will have only one element. The order of the matrix shown here is 1 by 3. The general representation of a row matrix having n columns is shown here. A matrix is said to be a row matrix if it has only one row. A matrix having equal number of rows and columns is called a square matrix. A matrix of order 3 by 3 is shown here. This matrix has 3 rows and 3 columns. General representation of a square matrix of order n by n is shown here. A matrix in which the number of rows is equal to the number of columns is said to be a square matrix. We will move to the next type of matrix. Consider a matrix where all the elements except the highlighted elements are zeros. These elements are called the diagonal elements of the matrix. These kind of matrices are called diagonal matrices. The general representation of a diagonal matrix is as shown here. Let's see how this general form is implied to the example shown. A square matrix is said to be a diagonal matrix if all its non-diagonal elements are 0. For a diagonal matrix, if all elements along the diagonal are equal to each other, then the matrix is called a scalar matrix. A scalar matrix can be represented as follows. Let's use the example matrix to understand the general form. This means that for I not equal to j, the element is 0. And for I equal to j, the element is a non-zero number k. A diagonal matrix is said to be a scalar matrix if its diagonal elements are equal. In a scalar matrix, if all the diagonal elements are equal to 1, then the matrix is said to be an identity matrix. Identity matrices of order 2 by 2 and 3 by 3 are shown here. Identity matrix is a special case of scalar matrix with the diagonal elements equal to 1. General representation of identity matrix is shown here. The general representation is used to explore the example as shown. A square matrix in which elements in the diagonal are all 1 and the rest are all 0 is called an identity matrix. When every element of a matrix is 0, the matrix is called a zero matrix or null matrix. A matrix is said to be zero matrix or null matrix. In this module, you will learn about the addition and subtraction operations performed on matrices. Arithmetic operations, such as addition and subtraction, are possible on matrices of the same order. However, the arithmetic operations are done on the elements of the matrices. Let's start by exploring the addition operation on two matrices. We have two matrices, X and Y, of the same order. If we are performing the addition operation on X and Y, it means that we are adding the elements of X to the corresponding elements of Y. Let's see how it's done. The element in the first row and the first column of matrix X is added to the element in the first row and the first column of matrix Y. Similarly, the other corresponding elements are added as shown. It has to be noted that matrix addition can be performed over matrices having the same order. If X and Y are two matrices of the same order, say M by N, then the sum X plus Y is defined as a matrix Z of the same order, where Zij is equal to Xij plus Yij for all values of I and j. An example of the addition operation over two matrices A and B is shown here. The sum operation is shown here. Every element of A is added to the corresponding element of B. The sum of the matrices A and B is as shown. The addition operation over matrices satisfies the commutative law and the associative law. First, we will look at the commutative law. If the matrices X and Y are of the same order, m by n, then X plus Y is equal to Y plus X. When we add the matrices X and Y, we actually add the corresponding elements of the two matrices. We know that the addition of numbers satisfy the commutative property. Therefore, the sum of the elements can be written as shown, which in turn is equivalent to Y plus X. Now, let's look at the associative law. If the matrices X, Y, and Z are of the same order, m by n, then X plus Y plus Z is equal to X plus Y plus Z. Let's verify the associative law over matrix addition. This proves that the addition operation over matrices satisfies the associative law. An additive identity exists for a given matrix. Let X be an m by n matrix and let O be an m by n zero matrix. Then X plus O is equal to O plus X, which is equal to X. In other words, O is the additive identity for matrix addition. Let's verify the additive identity. Similarly, the additive inverse of a matrix can be defined. Let X be any matrix. Then we have another matrix as minus X such that X plus minus X is equal to minus X plus X, which is equal to O. So, minus X is the additive inverse of X or the negative of X. Here, O is a zero matrix. A matrix can be multiplied by a scalar. Here, a scalar is any real number. The idea behind scalar multiplication is similar to the multiplication operation over two numbers. For example, if we multiply two numbers, A and B, we are adding A, B number of times. Similarly, when we multiply a matrix X with a scalar A, we are adding matrix X with itself A times. If A is a matrix of the order m by n and K is a scalar, then Ka is another matrix of the same order, which is obtained by multiplying every element of A by the scalar K. Let's see an example. X is a matrix. We will multiply the matrix with a scalar 4. The resulting matrix is 4x as shown. Based on the multiplication of a matrix by a scalar, we can define the negative of a matrix. The negative of a matrix X is defined as minus X. The negative of a matrix X is obtained by multiplying it with the scalar minus 1. We will now see some properties of scalar multiplication. If A and B are two matrices of the order m by n, and K and L are two scalars, then their multiplication will have certain properties. Let's look at the first one. K multiplied by A plus B is equal to Ka plus Kb. This can be proved as shown. Now, let's look at the second property. K plus L multiplied by A is equal to Ka plus La. This can be proved as shown. Similar to the addition operation, the subtraction operation can be performed over two matrices. Shown here are two matrices X and Y, which we used earlier. The subtraction of matrix Y from matrix X is denoted as shown. The resulting matrix is Z. The subtraction operation over matrices X and Y is shown here. The resultant matrix Z is of the form shown here. We will see an example of subtraction using matrices A and B that we saw before. The subtraction operation is shown here. Every element of B is subtracted from the corresponding element of A. The difference of the matrices A and B is as shown. If A and B are two matrices of the same order, say M by N, then the difference A minus B is defined as a matrix D. In other words, D is equal to A minus B, which in turn is equal to A plus minus 1 multiplied by B. That is, the sum of matrix A and the matrix minus B. It has to be noted that the subtraction operation is not commutative. In this module, you will learn about the multiplication operation over matrices. The multiplication of matrices is not similar to their addition or subtraction. In the addition and subtraction operations over matrices, we perform the operations element by element. In multiplication, however, we multiply the elements in a row of the first matrix by the elements in a column of the second matrix. Let's see the procedure. We have two matrices X and Y. Let the resulting matrix of the multiplication of these matrices be Z. We will first multiply the elements in the first row of X to the corresponding elements in the first column of Y. We will write the sum of the products of the elements as shown. Then, we multiply the elements in the first row X to the elements in the second column of Y. We will write the sum of the products of the elements as shown. In similar manner, we multiply the elements in the other rows and columns. Finally, we get the matrix as shown. Let's see an example with the matrices shown. First, we will take the first row of A and the first column of B and multiply the elements one by one as shown. Similarly, we multiply all the rows of A with all the columns of B. we get the resulting matrix as shown. Here, we have to note that the multiplication operation is possible only when the number of columns of the first matrix X is equal to the number of rows of the second matrix Y. If we have two matrices, X and Y, with orders m by p and p by n, respectively, then the product of the two matrices is of the order m by n. We can generalize the discussion. Let X be a matrix of order m by p and Y be a matrix of order p by n. Let the product of these matrices be equal to matrix Z, which is of the order m by n. Each element of matrix Z is given by the expression shown. In the expression, Zij represents the element in the ith row and the jth column of matrix Z. This is obtained by multiplying the ith row of matrix X with the jth column of the matrix Y. It should be noted that the multiplication operation over two matrices does not satisfy the commutative property. This means X multiplied by Y is not equal to Y multiplied by X. However, there are some cases that we need to look at. X multiplied by Y is defined, but Y multiplied by X is not defined. Let's see an example with the matrices as shown. The matrix X is of the order 2 by 3, while the matrix Y is of the order 3 by 3. Since the number of columns in X is equal to the number of rows in Y, finding the product of X and Y is possible. On the other hand, the number of columns of Y is not equal to the number of rows of X. Therefore, product YX is not possible. Sometimes, product XY and YX are both defined, but XY does not necessarily equal YX. Let's verify the case with the matrices shown. X and Y are 3 by 3 matrices. X multiplied by Y is as shown. Y multiplied by X is as shown. We can observe that though XY and YX are both defined, the matrices are not equal. If the matrices being multiplied are diagonal matrices and are of the same order, then the multiplication is commutative. Let A and B be two diagonal matrices of the order 3 by 3. Let's find the products AB and BA. We can observe that AB is equal to BA. Next, we will move to the case where the product of any two matrices is equal to a zero matrix. This does not always imply that either X is a null matrix or Y is a null matrix. Let's verify using an example. The product of these two matrices is a null matrix. We can observe that though matrices X and Y are not zero matrices, XY is a zero matrix. The multiplication property over matrices satisfies the associative law and the distributive law. According to the associative law, if we have three matrices X, Y and Z, then X multiplied by Y multiplied by Z is equal to X multiplied by Y multiplied by Z, whenever both sides of the equality are defined. Let's see an example to verify the associative law using matrices A, B and C. First, we will find the left-hand side. Next, we will multiply this matrix with C. We get the matrix as shown. Next, we will find the right-hand side. First, we will calculate the product of matrices B and C. Next, we will multiply A with this matrix. Both the matrices are equal. We can see that the multiplication satisfies the associative law. According to the distributive law, if X, Y and Z are three matrices, then X multiplied by Y plus Z is equal to X multiplied by Y plus X multiplied by Z. Also, X plus Y multiplied by Z is equal to X multiplied by Z plus Y multiplied by Z whenever both sides of the equality are defined. Now, let's verify the distributive law for the multiplication of matrices with matrices A, B and C as shown. First, we will find the left-hand side starting with A plus B. Next, we multiply this matrix with matrix C. Next, we find the right-hand side starting with the product of A and C. Next, we will multiply B and C. Next, we will add both the matrices. Hence, the distributive law is applicable to the multiplication of matrices. Multiplicative identity exists for any square matrix. If X is a square matrix, there exists an identity matrix I of similar order such that X multiplied by I is equal to I multiplied by X is equal to matrix X.
Suppose we have a matrix. If we interchange the rows and columns of this matrix, we will get a new matrix. This is called the transpose operation. This matrix is called the transpose of the first matrix. To understand this, let's find the transpose of matrix A as shown. Let the matrix that we obtain after transposing A be B. Let's see how we obtain this matrix. The first row of matrix A becomes the first column of the matrix B. Similarly, the second row of A becomes the second column of B. Now, the completed matrix is the transpose of A. The transpose of a matrix A is denoted as shown. An alternate representation of the matrix is written as A superscript T, where T denotes the transpose. It should be noted that the order of the matrices is of importance. If the order of the original matrix is m by n, then the transpose is of the order n by m. Now, we can define the transpose of a matrix. If A, B and m by n matrix, then the matrix obtained by interchanging the rows and columns of A is called the transpose of A. Now, we discuss some properties of transpose of matrices. We will now verify these properties with the help of examples. According to the first property, the transpose of a matrix is equal to the matrix itself. We will verify this with the matrix X. Let's find the transpose of X. Next, we will take the transpose of X. We observe that it is equal to X. The second property states that the transpose of the product of a matrix and a constant is equal to the transpose of the matrix multiplied by the constant. Let's verify this using the matrix Y by finding the left-hand side. We multiply Y by a constant, 5. Next, we will take the transpose of this matrix. Now, we find the right-hand side by taking the transpose of Y. Then, we multiply this matrix by 5. You can observe that the left-hand side is equal to the right-hand side. The third property states that the transpose of the sum of two matrices is equal to the sum of the transpose of matrices. First, we will find the left-hand side of the relation. The sum of matrices X and Y is as shown. Now, we will take the transpose of the matrix. Next, we will find the right-hand side by adding X transpose and Y transpose. We can see that the left-hand side is equal to the right-hand side. We will verify the fourth property by taking the matrices as shown. Let's find the left-hand side. First, by finding the product of matrices X and Y. Now, we will take the transpose of matrix AB. Next, we will find the right-hand side. First, we will find the transpose of matrices X and Y. The product of Y transpose and X transpose is as shown. You can see that both the sides are equal to each other. Based upon the transpose operation of a matrix, we can observe some properties of matrices. Suppose we have a matrix as shown. Let's find the transpose of the matrix. We can observe that the transpose of the matrix is the same as the original matrix. We can say that X is a symmetric matrix. We can now define a symmetric matrix. A square matrix A is said to be a symmetric matrix if its transpose is equal to itself. Let's observe another property associated with the transpose of a matrix. Let's find the transpose of the matrix, shown here. We can observe that the transpose is equal to the negative of the matrix. In this case, Y is called a skew-symmetric matrix. A square matrix is said to be a skew-symmetric matrix if its transpose is equal to the negative of itself. Consider the two matrices. Now, for any element in Y, the corresponding element in Y transpose is of negative value. We can observe that any element Aij in Y is equal to minus Aij in Y transpose. If I is equal to J, then we have Aii is equal to minus Aii. Therefore, we have 2 Aii is equal to 0, or Aii is equal to 0. It means that all the diagonal elements in a skew-symmetric matrix are equal to 0. This is evident in matrix Y. Next, we will see two theorems based on symmetric matrices and skew-symmetric matrices. The first theorem states that for any given square matrix A with real number entries, the sum of A and A transpose is a symmetric matrix, and A minus A transpose is a skew-symmetric matrix. A is a square matrix with real numbers as its elements. For the moment, let X be the sum of matrices A and A transpose. If X is a symmetric matrix, then X is equal to X transpose. Let's substitute A plus A transpose in place of X in X transpose. Using the properties we have seen earlier for transpose of a matrix, we can see that the right-hand side can be represented as shown. This implies the right-hand side is equal to A transpose plus A. This indeed is equal to X. Therefore, X is a symmetric matrix, or A plus A transpose is a symmetric matrix. Similarly, we can prove that A minus A transpose is a skew-symmetric matrix. Let us denote this matrix with Y. If Y is a skew-symmetric matrix, then Y transpose is equal to the negative of matrix Y. Let's substitute A minus A transpose in place of Y in Y transpose. Using the properties we have seen earlier for the transpose of a matrix, we get A transpose minus A. Upon rearrangement, we find that this is equal to the negative of matrix Y. Therefore, Y or A minus A transpose is a skew-symmetric matrix. Let's verify the theorem with an example by using matrix A as shown. The transpose of A is also shown. First, let's verify whether A plus A transpose is a symmetric matrix. The matrix A plus A transpose is as shown. If we take transpose of this matrix, we find this equal to the matrix A plus A transpose, which verifies the first part of the theorem. Next, we will verify that A minus A transpose is a skew-symmetric matrix. Let's take the transpose of the matrix. We can observe that the transposed matrix is the negative of A minus A transpose, which verifies the second part of the theorem. The second theorem states that any square matrix can be expressed as the sum of a symmetric and a skew-symmetric matrix. Let A be a square matrix with real numbers as its elements. From the previous theorem, we know that A plus A transpose is a symmetric matrix, and that A minus A transpose is a skew-symmetric matrix. We will multiply each of these matrices by 1 upon 2 and add them. We will use the property shown here to simplify the sum of the matrices. Hence, the theorem is proved. We can perform row and column operations on a matrix. These operations are particularly helpful when finding the inverse of a matrix, solving a system of linear equations, and finding determinants. There are 6 operations available on a matrix, 3 on rows and 3 on columns. Before we start with the operations, we will see some conventions. Suppose we have a matrix A with m rows and n columns. We denote the ith row as R subscript I and the pth column as C subscript P. Now, let's start exploring the operations. The first operation is the interchange of rows or columns. We have a matrix A. Let's interchange rows Ri and Rj. This is represented by a notation as shown. The symbol signifies the interchange of rows. Therefore, matrix A after the operation is as shown here. Let's see an example. Here, we have interchanged rows R2 and R3. Now, let's interchange the columns of a matrix. Here, we have interchanged the elements of the columns CP and CQ. An example is shown here. If we interchange the first and second columns, we get the matrix as shown. We will now see how the elements of a row or a column are multiplied by a non-zero number. If we multiply the ith row of a matrix with a non-zero constant, k, then the notation is as shown. For matrix A, if we multiply the ith row with a non-zero element, k, the resulting matrix is as shown. An example of a matrix whose first row is multiplied with 1 divided by 5 is shown here. If we multiply the pth column with a non-zero element L, then the resulting matrix is as shown. A matrix whose second column is multiplied by 4 is shown here. Next, we will see how the elements of a row or a column are added to the corresponding elements of any other row or column multiplied by a non-zero number. Suppose we want to add the elements of the ith row to the corresponding elements of the jth row multiplied by a non-zero element, k. The operation is written as shown. Let's see how it performs over matrix A shown here. First, we will multiply the jth row with the non-zero constant k. Then we add these elements to the corresponding elements in the ith row. Let's see an example. Here, we have replaced the second row of the matrix according to the operation. A similar type of operation over the columns of a matrix is shown here. In this operation, we are replacing the elements of the pth column with the corresponding elements of the pth column, plus the elements of the qth column multiplied by a non-zero constant L. Let's see how this is done with the help of matrix A. According to the operation shown, we will replace the pth column with a new column. After the operation, matrix A becomes like the one shown here. Let's see an example. Here, we have replaced the elements of the first column with the corresponding elements obtained by the operation. Suppose we have a square matrix A of the order n by n. If we multiply this matrix with another matrix of the same order and the product results in an identity matrix, then the other matrix is called the inverse of matrix A. Here we can say that matrix A is invertible. Therefore, we can define the inverse of a matrix. If A is a square matrix of order m, and if there exists another square matrix B of the same order m, such that A multiplied by B is equal to B multiplied by A is equal to the identity matrix I, then B is called the inverse matrix of A. We have to be careful with notation used for the inverse of a matrix. The inverse of a matrix A does not mean that it is 1 divided by matrix A. It should be noted that a rectangular matrix does not have an inverse matrix, since for products AB and BA to be defined and to be equal, it is necessary that matrices A and B should be square matrices of the same order. It should also be noted that if matrix B is the inverse of matrix A, then matrix A is also the inverse of matrix B. There exists only one inverse for a given matrix. The theorem states that if the inverse of a matrix exists, it is unique. Let A be a square matrix of the order n by n. Let X and Y be inverse matrices of A. Therefore, the product of matrices A and X is equal to the identity matrix I. Similar is the case with matrix Y. Now matrix X can be expressed as the product of X and the identity matrix of the same order. This relation can be expressed as shown. Therefore, X is equal to Y. Now, we will prove a theorem on the inverse of the product of two matrices. Let's start with the left-hand side. We know that the product of the matrices AB and AB inverse is equal to the identity matrix. Let's multiply with A inverse on both the sides. Since matrix multiplication is associative, we can arrange the left-hand side of the relation as shown. Now we can simplify as shown. Now we multiply with B inverse on both the sides. This can be simplified as shown. Therefore, the inverse of the product of matrices A and B is equal to the product of matrices B inverse and A inverse. Now, let's look at the method where we will find the inverse of a matrix with the aid of elementary operations. Let's see the idea behind finding the inverse of a matrix by elementary operations. Let's consider a matrix A. We can express this matrix as a product of a unit matrix and itself. We saw that a matrix multiplied by its inverse is equal to the identity matrix. We can relate the two relations as shown. Here, you can see that if we can transform the left-hand side into an identity matrix, then by the transformation process, we automatically obtain the inverse. The transformation is done by using either row operations or column operations. If we perform the row operation, we will represent the relation as shown. On the other hand, if we perform the column operation, we will represent the relation as shown. Now, we will find the inverse of a matrix using both row and column operations. Let X be a matrix as shown. We can express this matrix as shown. Since matrix X is represented as identity matrix multiplied by X, we will perform row operations until the matrix on the left-hand side transforms into an identity matrix. The operations are as shown. Therefore, the inverse of matrix X is as shown. Now, we will obtain the inverse of the same matrix X using column operations. When we want to perform column operations to find the inverse, we should express matrix X as X multiplied by the identity matrix. Now, we will perform column operations until the matrix on the left-hand side transforms into an identity matrix. Now, we have obtained the identity matrix on the left-hand side. The inverse of matrix X is as shown. It can be easily seen that the inverses obtained by either row or column operations are the same. Note that, while we perform row and column operations, if all the elements of a row or column are obtained as 0, then the matrix has no inverse.